In this section, we're going to look at a method of integration called substitution, and it's going to expand the types of integrals that you can evaluate. Just a quick little warm-up here so you can see the need for this method that we're about to talk about. In question number 1, I'm asked to do the antiderivative of cosine x dx, and I know that cosine x is the derivative of sine x. And because this is an indefinite integral, that is, there are no limits, I know I have to put the plus c at the end to represent that constant that I can't recover in this antiderivative process. I'm also asked to check my answer by differentiating. And I know that any antiderivative can be checked by doing the derivative of the answer. Derivative of sine x is the cosine x. Derivative of that constant is 0, and that checks out with my original problem. In question number 2, I'm asked to find the antiderivative of cosine of 5x. So instead of just having an x, it now is a 5x. You might want to think, I might just replace the x with the 5x. So let me take a guess at this antiderivative first. So let's go ahead and check out this answer. Antiderivative of cosine 5x dx is sine 5x plus c. I should be able to take the derivative of my answer and end up right back with the original problem. Let's check that out. So here, if I do the derivative of my answer, sine of 5x plus c, when I do the derivative of sine 5x, I have to engage the chain rule. So it's going to look like this. When I do this derivative of the outside, that's the cosine, leave the inside alone as the 5x, times derivative of the inside, puts this multiplying by 5. What I see is that what I got when I did the derivative is not what I started with, which means that my antiderivative is incorrect. I have this extra multiplying by 5 here at the end that didn't show up in the original problem. So I can balance that out pretty easily by just multiplying by 1/5. And so my answer here is actually a 1/5 sine of 5x. This method of substitution will be used when the derivative was obtained by using a chain rule. So let's go ahead and review the chain rule. We used that when we were doing the derivative of a composite function, a function inside of another function. F is the outside function, g of x is the inside. We did derivative of the outside as the f prime. Leave that inside function alone, so that just stayed g of x, times the derivative of that inside function. So when I do the derivative of f of g of x, I get this f prime of g of x times g prime of x. So now, just using your knowledge of the relationship between integrals and derivatives, if I do the antiderivative of that answer, you know that I'm going to end up right back with what I started with over here, plus that extra constant of integration, that plus c at the end. The substitution method is going to give us a methodical way of finding these antiderivatives. I've got the steps listed out here, and we will just kind of follow through them. What I want to show you is that statement above. We're going to prove that it's true, and we're going to go through these steps as we do it. We are going to be finding the antiderivatives of integrands that follow this format. They are the result of a chain rule. The first step you're going to do is look for an inside function. So when I look at this, I can see that g of x is my inside function. I'm going to do a change of variable, and I'm going to call this u, and that's our step 1. We're going to let u equal that inside function. Step number 2 says let's do the derivative of u with respect to x. So I'm going to look here. I'm going to do that derivative of u with respect to x. I'm going to use that Leibniz notation. And I know the derivative of g of x is g prime of x. The next thing I'm going to do is take this dx, it's called a differential, it's on the bottom, and I'm going to multiply it to the other side. What I'm trying to do is get this integrand in terms of a new variable that I'm calling u. So at this point, I'm going to do a lot of substitutions. I have here that g of x equals u. So that means here, this g of x, I'm going to replace it with a u. And then I also have a g prime of x dx. Notice that's exactly what I have right here. And that means that whole green part, the g prime of x dx, can be replaced with the du. Switching to this new variable u greatly simplifies that integrand. So now I'm just finding the antiderivative of f prime of u du. There's an important note over here in step 3. When we're sitting at this step after you do all your substitutions, your integrand should be solely in terms of u. There should be no x's left. So now the question is, f prime of u is the derivative of what? And we know the answer to that is f of u. And that's what this step 4 is asking me to do. Don't forget your constant of integration, that plus c. Our last step is step 5 here. It just wants us to get this back in terms of x. So that original substitution I did of letting u equal g of x, I'm just going to go back and replace the u back to g of x. And you see that process put me right back to that composite function. If that felt confusing, it'll just take a few examples and then you'll get the hang of it. The first thing we need to do is recognize the need to use a u substitution when I have a function inside of a function. So it's this 5x inside of that cosine function that tells me I need to use a u substitution. And my first step is to let u equal that inside function. Step number 2 says, let's do the derivative of u with respect to x. And then we're going to take this dx and we're going to multiply it to the other side. Every problem is going to start similar to this, defining the u, finding its derivative, and bringing that dx over to the other side. When you get to this point in the problem, start planning out your substitutions. What I can see is the 5x is right here. So I'm going to substitute my u in place of that 5x. Remember, our goal is to switch this whole integrand to be a variable u instead of an x. What I still have left in terms of x is this dx. What I've got going for me over here is a 5dx. I want to try to get them to match. So right here I need to isolate this dx, and that's going to take me dividing by 5. So my dx replacement is going to be this 1/5 du. And it looks like this. Notice that I don't have any x's left. It's all in terms of u now. My next move is to take that 1/5 and pull it to the outside. Now I just find the antiderivative of cosine u du. That gives me 1/5 sine u plus c. My last move is just to get this back to my original variable. So in place of that u, I go back to my original definition up here, and I put that 5x back in. As you see, this is the same answer I got in the warm-up above. This just provided me a more methodical, step-by-step way of arriving at that answer. Also, don't forget we can check any of these by finding the derivative of our answer. So on this one, I could just quickly do a derivative of this one. So I have 1/5. The derivative of the sine is cosine. Leave the inside alone is the 5x, times derivative of the inside is the 5. The 1/5 and the 5 will cancel each other out, and I get cosine 5x, and that's what that original problem was, which assures me my answer is correct. And because that was so much fun, let's do another. I see in number 2, I have an inside function, the 7x minus 4 is inside of that 5th power function, so I'm going to let u equal 7x minus 4. Here's my definition of u. Here is my derivative of u with respect to x. Then we take that dx and we swing it over to the other side. When you get to this point, you stop and plan your substitutions. I could see the 7x minus 4 is going to be my u. I also need to replace this dx. What I have going for me is a 7dx. That tells me I need to divide by that 7. And my dx replacement is this 1/7 du. I move my 1/7 constant multiple to the outside of my integral sign, and now I'm ready to do my power rule. So just add 1 to my power, divide by the new power. And my last step is to replace the u with that original definition of u, which was that 7x minus 4. And I went ahead and multiplied those denominators together as well and got that 1/42. In question number 3, this time I'm going to let u equal that 2x. And here's my derivative with respect to x, and bringing that dx over with the 2. It's here where I stop and plan where I'm going to put things. And I can see up here the 2x, well, that's just going to be my u. Here I have a 6dx, and here I have a 2dx. In order to get those to match, I can multiply both sides of this by a 3. That tells me that this 6 dx can be replaced with a 3 du. I went ahead and pulled that 3 to the outside of the integral sign, save myself a step. I know that the antiderivative of e to the u du is just e to the u. And then my last step is just to get this back in terms of x, so I'm just going to put that 2x back in place for the u. That gives me my final antiderivative answer. Let's do a quick check by doing the derivative and see if we end up with our original problem. This is an exponential, so I know my derivative is just write down what I see. So 3e to the 2x times the derivative of the exponent. It's going to be times the 2. That gives me 6e to the 2x, and that's what I started with, so check, my answer looks good. Question number 4 looks complicated until you analyze what's going on, and then it's pretty cool. So I look at this, and it looks like a very complicated integrand. I do see that this 2x squared minus x is inside of that fifth power function. So let me let that equal my u. This part of the problem is all pretty standard. When you get to this part, stop and plan out where you're going to substitute things. I see that my 2x squared minus x, that is going to be my u. The other parts that need replacing is this 4x minus 1 dx, and that's exactly what I have sitting over here, which means this whole piece right here gets replaced with my du. This complicated integrand that I was faced with initially has actually simplified greatly, and now I can do an easy antiderivative of this one. Simplifying and getting this back in terms of x gives me my final antiderivative. On example number 5, I'm first going to rewrite that cosine cubed x as cosine x quantity cubed. And now I can see that that cosine x is my inside function. Notice I streamlined this a little bit, so instead of that step in here that said du over dx, I just went ahead and put the dx over here, and that's okay for you to do. It's at this step that I start planning out my substitutions. My cosine x is going to be the u. I take a look at what else needs replacing, and it says sine x dx. What I have over here is a negative sine x dx. That tells me I need to do something with that negative. What I'm going to do is multiply or divide by, just move it to the other side. This became u to the third power. This negative 1, I went ahead and put it in the front and ended it with the du. Now my antiderivative is just a simple power rule. And then I do my antiderivative, plug my cosine x back in, and that is my final antiderivative. When I look at question 6, there's nothing that's striking me as an inside function. This is one of the hints that I have in the margin. Number 3 says, consider u equals the denominator. So that's what I'm going to do on this one. I'm going to let u equal that 4x plus 5. If we go ahead and look ahead here for a second, if I'm going to put a u down there in the denominator, and this is going to be something over u, what I'm going to be looking at is a natural log as my antiderivative. On this one, I'm going to go ahead and take that constant multiple, that 3. I'm going to pull it to the outside right now. So I've got my 3 pulled to the outside. I've got my 4x plus 5 replaced with the u. What I have left is this dx that I need to replace. Over here I have a 4dx. That tells me I need to divide by that 4. And that gives me my dx replacement. My dx was replaced with the 1/4 du. Went ahead and pulled that 1/4 to the outside. Now I'm just looking at this integrand, and this is a simple one. This is the derivative of the natural log of u. Don't forget your absolute value around your u. My last move is just to put my 4x plus 5 back for the u. And this is my final answer. And again, if you just wanted to give it a quick check, I would just do a quick derivative to check it. I know my natural log derivative is just 1 over that argument, so 1 over 4x plus 5, times the derivative of 4x plus 5, which is times of 4. That constant multiple in front, that 3/4, is just carrying down. And then I can see that my 4's are going to wipe each other out, and my final is exactly what I started with, so that means my antiderivative looks good. All right, one last question here. In question number 7, my first job is to define what u is. I'm going to let u equal strictly what's inside that square root sign. So 2 minus r to the fourth. Taking the derivative gives me negative 4r cubed dr. Notice I just jumped a step ahead. Instead of doing du dr, I went ahead and just put the dr over to the other side. What I do now is I compare what I have to replace. I can see that my 2 minus r to the fourth, my 2 minus r to the fourth is here. So that's going to go inside that square root in the denominator. The other parts that need replacing is this 8r cubed dr. What I have going on over here is a negative 4r cubed dr. If I want to replace it, I need an exact replacement. So I can just think about what do I need to do to this negative 4 in order to get it to equal the positive 8, and that would be to multiply by negative 2. So I'm going to multiply both sides by negative 2. And when I do that, I get an exact replacement for my 8r cubed dr. I'm going to replace it with this negative 2 du. So that whole numerator gets replaced with a negative 2 du. And now that I've converted this strictly to my variable u, I just go ahead and do my antiderivative. It's going to involve bringing this square root of u up to the numerator and rewriting it with a rational exponent first. I'm now ready for the power rule, so I'm going to add 1 to the power and divide by the new power. Next, I'm going to simplify this a little bit and also put my 2 minus r to the fourth back in for my u. And here is my final antiderivative. In doing these problems, half the battle is being able to select the correct expression for u, and sometimes it might take several restarts in order to pick the right one, but you just have to keep going and keep trying, and you'll get the hang of this. And the secret, just like anything else in math, is the more of these you do, the more practice you get, the better you're going to be at it.